This work explores techniques for manipulating near-regular textures in novel ways. We manipulate textures with geometric, lighting, and color deformation fields. Here we demonstrate our algorithm for extracting and manipulating geometric deformation fields from a near-regular texture. Relating this near-regular texture to its regular origin, we first identify its distorted underlying lattice, in this case, interactively. We then straighten out the distorted lattice into the nearest regular lattice, such that we have a type 1 regular version of the input texture. We compute the geometric deformation field between the near-regular lattice of the input texture and the regular lattice. Given the duality of the deformation field, we can also treat this functional deformation as a texture in its own right. Here it is viewed in an HSV color space. Here we alter the geometry gain in order to manipulate the magnitude of geometric deformation in the synthesis results. Here we use lighting deformation fields for texture replacement, synthesis, and analogy. Our first task in analyzing an input texture is to compute its type 1 regular lattice and the corresponding geometric deformation field. On the type 1 texture, the user specifies a canonical lighting region, where a piece of regular texture is evenly lighted. A texture model under normal lighting is constructed based on texture samples in this canonical lighting region. This model is then used to extract the lighting effects across the whole type 1 texture surface. We are able to apply the deformation field pair to other textures to achieve the effect of texture replacement under the same lighting. Furthermore, we can synthesize both geometry and lighting deformation fields jointly to cover a larger surface. It is observed that the lighting and geometry deformation of a near-regular texture have a strong association on images taken in a realistic environment. We use the image analogy technique as a medium to achieve a deformation field analogy. This method allows us to believably light an arbitrary geometric deformation field. Our final deformation field color models the color space variations between tiles in an input texture. This input brick texture has 12 tiles. Before computing color deformation, we geometrically deform the input texture to regularize the tile set. Once tiles have been geometrically aligned, PCA can be used to model the irregularity between tiles. First, the mean tile is calculated and subtracted from the tiles. The outputs from PCA are several basis tiles and the appropriate coefficients for these tiles used to recreate the input tiles. We can create a generative model of the texture's tiles by examining the distribution of input tiles in PCA space and sampling randomly within the same range. We can also vary the regularity of our generated tiles by changing the way we sample the PCA space. We use the color gain parameter to affect the amplitude of color irregularity expressed in the generated tiles. We can now create an infinite number of tiles for use in near-regular texture synthesis. This is a synthesized brick wall texture using 1,400 unique synthetic tiles. Our texture synthesis algorithm can be applied to texture replacement in real images. The goal is to replace a near-regular texture in an image while preserving geometry, deformation, lighting effects, and shadows. First, we extract the near-regular tiles from the input image. Next, we regularize the lattice through geometry deformation. We define our canonical tile in order to calculate lighting deformation. Now we have the necessary deformations to insert any new texture in place of the original near-regular texture. Here we replace the wall texture with the previously shown brick synthesis result. The bricks currently have 0 geometry and color gains. Here we alter the brick texture's geometry and color gains. Color gain is simply another coefficient to the basis tiles for each generated tile. Irregularity is extrapolated beyond what was seen in the input tiles by setting color gain above 1. We can also mix and match deformation fields. In this case, we use the geometric deformation field from the snakeskin texture. Using our geometry and lighting deformation fields, we can substitute any image or sequence of images for the original near-regular texture.